Hi y'all, this is Mel. Welcome back to Heat and Mass Transfer. Today we're going to be doing problem 9.001 out of the textbook. So with this one, it's a 1D plane wall from chapter 3. It's got a thickness of 75 millimeters and a thermal conductivity of 2.5 watts per meter Kelvin. On each side, actually got a sketch down here. On each side, we have a fluid on one side and a fluid on the other side. They have different temperatures. Um, In this case, we're going to be assuming they actually have the same heat transfer convective coefficient, but we know they have different temperatures. We also know what we're looking for is we're looking for the minimum and maximum steady state heat fluxes using the values in table 1.1 for free convection in gases, free convection in liquids, forced convection in gases, forced convection in liquids, and convection with phase change. We're assuming negligible radiation and no contact resistance between the fluid and the wall. Two others that I did not write down but that are fairly relevant to this is that it's going to be steady state, so there's no energy stored, and also that it is the word, no heat generation, so the wall's not magical, it's not generating heat. The solution is thermal resistances. We've got our T infinite, our bulk temp 1, surface 2, bulk temp 2. From there, we can calculate a net thermal resistance of the system from bulk temp 1 to bulk temp 2, because remember, we don't know the surface temperatures of the wall. And then we're going to use the Q equals, so this actually should be heat flux, it should be double prime. With the 1 over the resistance times the delta T of between the first fluid and the second fluid. And I actually ended up doing MATLAB for this because I didn't want to do all of this by hand and it's the same equation every time. So if we hop over to MATLAB, we've got this problem again. We've got our vector of convective coefficients. We've got these two are free convection in gases, forced convection or free convection in liquids, forced convection in gases, forced convection in liquids, and what the other one is. The last one was phase change. That's what it was, phase change. So we've got our bulk fluid temperatures. We've got our thermal conductivity of the wall, and we've got our thickness of the wall. We can calculate a conductive resistance, a temperature difference between the two convective ends of the thermal circuit. We've got, for every time the length of this vector, we're going to calculate for each value of, for each value of the convective heat transfer coefficient, we're going to be calculating a net resistance because the convective resistance changes with this convective coefficient. And we're going to calculate a heat flux from that equation from earlier with the 1 over R net times the temperature difference from the two fluids. If we run this, we're going to actually generate a table here that I have some names for. And so we're going to see a flux for gas free convection minimum value in the gas. With an H value of 2, we've got a flux of about 100 watts per meter squared. Maximum, it's about 1,000. And we actually see this change for all of the other situations listed here. If you'd like to pause this and take a screenshot, you're welcome to. So yeah, there's also phase change mentioned. Let me just see if I can I open this? Will it let me? One moment. No, that's worse. All right. Hide the code. Yeah, not better. All right. So yeah, we've got our tabulated values here for the heat flux across this wall for all of these different situations. Oh, now you let me view it. Come on. There we go. So we've got our free convection in gas, free convection in gas, minimum and max. Same here for liquid, gas forced, liquid forced, phase change, and min and phase change max. And there we go. That's how it be. Thank you for coming.